In this video, we will provide a general overview of shallow autoencoders. In PCA, we assume the data points live in a space of less dimensions. For example, we have points in a 2D space. The assumption is that they are generated from a line or subspace in one dimension. We can assume the data points live in a nonlinear space, called a manifold. This is similar to our line, our subspace as shown in the image. We have the points. We assume there is noise that make the points deviate from the manifold. Linear autoencoders are a generalization of shallow autoencoders. We have the encoder matrix with the same number of rows as the dimension in the latent space, and the same number of columns as input dimensions. In addition, the encoding function. This is just an activation function. This is a new latent space. This applies the activation function to each element. The decoder works in the same manner. Apply an activation function to decode the code H, or the decoding function. The dimensions of the decoder are transposed compared to the encoder. Generally, we would like for the input to approximate the output. We can use the mean squared error. There are other loss functions we can use that we will not cover in this course. We can use several activation functions for the encoding and decoding function. Linear activation. This would be used in PCA. Sigmoid, tanh. The ReLU had a 0 output. This may cause issues in the decoding process. As a result, we use the scaled exponential linear unit, or CELU. They have a small value for z, less than 0. The expression is given by the following parameters alpha and beta are used to be the default. Like PCA, we have undercomplete autoencoders where the latent space has less dimensions. In addition, we have overcomplete autoencoders where the latent space has more dimensions. Undercomplete autoencoders can be used to extract features or reduce the dimensions of data. Let's do an example to visualize data. The latent dimension can be seen as a feature generator. A good encoder should map each distinct number to a different region in the latent space. This can be used for visualization, or we can use this in tandem with a second model. For example, to classify the digits. The module or class is similar to a linear autoencoder. We just add the encoder function on the output. We can create a method to output the code. In this class, we apply the activation function after the decoder. Training the model is almost identical to a linear autoencoder. We use a train loader object in this case. We will calculate the loss. Overfitting can be an issue with nonlinear autoencoders and overcomplete autoencoders. So we track the cost on the validation data. For images, we will have to change the shape of the tensor. We create the dataset object as before. We create an autoencoder model with a tanh encoding function. We have our loss function. We have the learning rate and optimizer. We use the function to train the model. We see the cost on training and validation data. In the lab, we see how the outputs of the 3 variations of the autoencoder look. We have the input X. We have the autoencoder with the linear encoding and decoding function. We see the output looks similar, but there is some distortion. This is not surprising as the latent space is only 3 dimensions. We have the autoencoder with a tanh encoder function. The output looks similar to the linear function. Finally, we have the autoencoder with the encoding and decoding tanh function. As the output is in between -1 and 1, it does not do a good job of reconstruction. This decoding function is usually used with different loss functions. Generally, nonlinear autoencoders produce more robust features. Let's visualize the code. Each color corresponds to a different class. We see that the linear encoder is difficult to make out the class in the code. In the nonlinear encoder, each clusters appears to correspond to a different class. But nonlinear encoders can just copy the data points instead of learning useful representations. Finally, we have the code with the nonlinear encoder. It's difficult to see the clusters. Now let's see how we can use an overcomplete autoencoder for noise removal. Consider the following example. We have the following manifold. A manifold is similar to the line or plane we used in the previous examples, but it is not linear. In this case, it's a rectangle function. x1 is the horizontal axis, and x2 is the vertical axis. We have a data point in blue. we add noise to the horizontal and vertical component. We represent this with x tilde. We repeat this for multiple samples. We can estimate x from x tilde by using the encoder to reduce the noise. We have our encoder, the decoder. The autoencoder is overcomplete. The cost is determined to minimize the difference between the true sample x and the output of the autoencoder with the noisy x tilde as the input. This is x hat using our old notation. Let's do an example in PyTorch. We have the dataset object where we have the code to generate the samples x. X underscore represents x tilde. We follow the convention for the training and testing data that we used in our other dataset objects. The first output is the noisy x tilde. The second element is x. The training function is almost identical. We have the dataset object that outputs x tilde and x. We have the output. We calculate the loss. In addition to a linear autoencoder, we create a model with a CLU output. We create a dataset object for training and validation data. We create a training and validation loader. Now we create the autoencoder, loss function, optimizer with specified learning rate, and train our autoencoder, saving the results. Each row of the following table shows the linear undercomplete, nonlinear overcomplete, and nonlinear overcomplete autoencoder. We see the nonlinear overcomplete autoencoder has the best result on training and validation data. In the following plot, we see the noisy samples in blue and the manifold in green. The red line is the manifold after it's passed through the linear undercomplete autoencoder with one latent dimension. The orange points are the points after they pass through the autoencoder. We see the points and the manifold are mapped to a line. The next plot shows the linear overcomplete autoencoder with 10 latent dimensions. We see that the output does a better job, but the manifold is distorted in addition and the orange points do not fall on the manifold. Finally, we have the nonlinear autoencoder. We see the manifold more closely resembles the manifold, and the effect of the noise is minimal, as most of the points fall on the manifold. Like neural networks, we can increase the power of autoencoders by making them deeper.